Hello automation superheroes, my name is Andrew and welcome back to Controtek Solutions Online Superhero Academy. Our goal is to bring you a series of online demos, webinars, and all the technical know-hows about smarter industrial automation. In this episode of the Beckhoff programming series, I will discuss about the standard function blocks and structured text instructions in TwinCAT 3.
In the previous episode, I have discussed the IEC 61131-3 PLC programming standard, such as ladder logic, function block diagram, structured text instruction list, SFC and CFC. Taught you how to implement the ladder, FBD and structured text programming. I have also demonstrated how to create POUs such as programs, function blocks, functions, and actions. Now, this will be the outline of the topics on this video. We'll be discussing the standard function blocks such as bistable, timers, triggers, and counters, and also the structured text instructions. This includes structured text operators, if instruction, case instructions, and for loop. Today, I will be giving you an overview of those standard function blocks and structured text operators you can use in your TwinCAT PLC programming. So just a quick run through. Basically, what I did on the last video was I demonstrated basic bit logic operators. I made a ladder logic diagram for motor control, a simple start-stop program, and of course, that includes the bit logic operators such as assignment, OR logic, and also AND logic. I have also demonstrated how to test your program online, like writing values whether true or false, and also preparing values for integer or real data types. And also, there are a number of libraries available on TwinCAT. These libraries are classified depending on their functions and applications, whether it's for system, motion, control, which includes temperature, PID, connectivity, Modbus, and building automation. Each of those categories includes specific libraries for your requirement. Now, each library contains ready-made or prepared function blocks or any program organization units you can use in your program. In this video, I will be focusing on the standard library, which is included in the system category. The standard library includes all the IEC 61131-3 POUs. These POUs are classified as bistable function blocks, trigger function blocks, counter, timers, and more. I will discuss each of the standard function blocks, give a brief description, show you how to create them, load it, and simulate it to the target device. Okay, now I'll begin with the bistable function blocks. A bistable function block maintains its output in one of two stable states, true and false. The output can be set or reset by applying a true signal to the set or reset inputs. Those two standard bistable function blocks are called SR and RS, set dominant and reset dominant. I'll start with set dominant or SR function block. A set dominant function block in a PLC has two inputs, set and reset. With set having precedence, regardless of the condition of the reset input, the instruction will turn its output true on the rising edge of set and will remain on as long as set is true, regardless of the reset state. The output will continue on even when set is off until reset is true. As these are function blocks, an instance should be declared in the main program and can be assigned with an appropriate identifier. Here I have already prepared the function block for SR or set dominant. I'll name it SR1. It means I have now an instance of the set dominant function block named as SR1. I'll go in the action 02 underscore FBD and add another network below. So to call an instance of a function block, you just need to right click on the network you want that block to be added, then choose command insert empty box. An empty box looks like this. It is clearly undefined and a bunch of question marks is currently visible. This field above with question marks is for the identifier of the function block instance, or the name of that function block created on the main program. In my case, it should be SR1. So I just type in the identifier or copy paste it from the main program. If the identifier you assign for an empty box is valid, it will automatically update the box. Here we could see that it became an SR box and the input set and reset have been defined here in the left side and the Q1 output on the right. Now I have only two question mark fields. This is where you assign Boolean variables for the SR function block inputs set and reset. So going back to the main program, I have also declared Boolean test variables named btest underscore var. It is an array of 0 to 100. This means I have 101 Boolean variables ranging from array 0 to array 100. So all throughout this episode, as I demonstrate standard function blocks, I will just use these variables for testing or online simulation. I'll start with array 0. I'll assign btest underscore var 0 as the set input and btest var 1 as the reset. Build the project. And perform online change. To show you how this function blocks operates, I'll write a true value on the set input. Now, Q1 output is now true. Even if I make this variable false, the Q1 output will remain true. So basically, it latches the Q1 output. This Q1 output can only be in false if I write a true value for the reset input. Now, what if both of those signals simultaneously turns true? I'll write a true value on both variables for the set and reset inputs and command write. The Q1 output is still true. That is why it is called set dominant. If an event of both signals for set and reset becomes true, the set input will be dominant and the output Q will still be set to true, regardless of the state of the reset. However, the RS or reset dominant is the opposite. If an event of both signals for set and reset becomes true, the reset input will be dominant and output Q will be set to false. I'll add another network and also an empty box. So this box will now be my RS function block named as RS1 as declared here in the main program. Then I will assign a Boolean variable to the inputs. The last array value I used is btest underscore var1. So now I will start on array 2. And for the set input, array 2 and array 3 for the reset input. Build the project. And again, perform online change. So I'll demonstrate how this FB operates. I'll write a true value on the set input. As expected, the Q output will be set to true as well. Now I would write a false value on the set input. The output is still true, unless the reset variable is set to true. Now if both of these signals turns true simultaneously, the reset input will be dominant. Hence, the Q1 output will be on false. Now the following images you'll see is an example on how the two bistable FBs are called using structured text. In my given example, I have used function block diagram language. Also, I have added a ladder example as set, reset, coil operations. Next is the timers. I'll begin with the on-delay timer, or TON. As the word itself, on-delay means delayed on. This means that this function block will only give an output after a certain time has elapsed. And this certain time only runs while the input is active. To create instances of the TON timer or on-delay timer, it should be declared here in the main program with an identifier. In here, I have named my on-delay timer as TON1, and it is a TON type. So that is how you create or declare instances of the TON timer. Going back to the action, I have to add a new network below and also another empty box. Type in the name of my timer, TON1. The empty box will be updated to a timer. So as you can see, the on-delay timer has two inputs, in and PT. In is the input and PT is the preset time. The block also has two outputs, Q and ET. Q is the output of the block and ET is the elapsed time. I'll just assign a boolean variable for the input of the timer, and the preset time or PT, I'll just type in a constant time, for example 10 seconds. So the format would be like this: T, sharp symbol, 10, and S for seconds. So for example, this is the format of time. Next is the outputs. You can assign variables here at Q, and you can also assign a variable for the elapsed time, or you could just leave it on blank. So for me, I will assign a time variable on the ET so we can monitor the time. Okay, so build my solution. No errors, and click on login. Now, before I simulate the timer, here's a graphical representation to further understand how the on-delay timers operate. So what happens here is, if N is false, Q is false, and elapsed time is also 0. And as soon as N becomes true, the time will begin to be counted in milliseconds, that's in elapsed time, until its value is equal to the preset time. That will remain constant. Q will only be true if the ET, or elapsed time, is equal to the preset time. And that will only happen as long as N is true. If N becomes false and ET is not yet equal to PT, the timer resets back to 0. So here's how it works. So the preset time of my on-delay timer is 10 seconds. if I turn the input true, the timer should count to 10 seconds. After 10 seconds, the Q output will be true. Okay, so I'll just write a true value on my input. Command write. Then wait for the ET to be equal with PT. And the output will be true. And that's how the on-delay timer works. This is also how you call a timer in ladder diagram, function block, and in structured text. So in my example, it is in FBD form. Next is the off-delay timer. Now, this is the opposite of the on-delay. Instead of having a delayed on of the timer output, this one is delayed off. As simple as that. Going back to the main program, I already have declared also a TOF timer named TOF1. And just additional information, you can also declare or create instances of function blocks as array. In case you require a lot of timers in your program, it's easier to declare arrays, but it is still completely up to you on how to make an efficient declarations of your variables and instances of your function blocks. So next, what I'm gonna do is I need to call my off-delay timer in the FB action. So it's the same procedure as I have previously did. Again, before I simulate the off-delay timer, here's a graphical representation to further understand how the off-delay timer operates. So when in is true, Q is true, and ET is 0. And as soon as in becomes false, the time will begin to be counted in milliseconds in ET until its value is equal to that of the PT. It will then remain constant. Q is false when in is false, and ET is equal to PT. Otherwise, it is true. Thus, Q has falling edge when the time indicated in PT in milliseconds has run out. So here's how it works. Now, what I did is I assigned the same Boolean variable I used on the on-delay timer above, so we could see the difference between TON and TOF. Also, the preset time of each timer is set to a constant value of 10 seconds. Okay, so let me just turn the input into true. Write the true value. As you can see, the output of the on-delay is not yet true, while the off-delay is already true. Now that both of the output is true, let me set the input into false. As soon as the input of the on-delay timer is false, the output is also false. While in the off-delay timer, it waits for the ET to be equal to PT before the output turns false. So yes, basically the output is delayed off. Here's also a sample on how to call an off-delay timer in ladder, function block diagram, and in structured text.
Now let's talk about triggers. Triggers are standard function blocks that detect either a rising edge or a falling edge of an input and sends an output for one execution only. A rising edge is the transition of a signal from low to high, 0 to 1, or false to true, while the falling edge is the transition of signal from high to low, 1 to 0, or true to false. So let's talk about the R-trig first. So it is a block that detects a rising edge, then gives an output of one execution only, or we can describe it as a single pulse. Now, this is how you create an R-trig function block in the main program. As you can see, I have created an R-trig1 as an identifier, and it is a R_trig. To call this function block, same procedure as the previous. Add a new network. Insert an empty box. Then type in the name of this box as R-trig1. The box updates to an R-trig. So this block has one input and one output. The CLK detects the rising edge and outputs it to Q. Next is I will assign a Boolean variable for the CLK input. Once the output sets true, we will not be able to see it with our eyes because the execution is very fast. So what I'm going to do is I will connect the output to an SR block so we could see at least that it operates properly and have sent one output latch the Q of the set dominant block. Build the solution. And download. Here is also a graphical representation of the R-trig. So the output Q will remain false as long as the input variable CLK is false. And as soon as CLK is true, the block detects a rising edge. Q will be true for only one execution. And when CLK detects another rising edge, it will again give a true value of Q. Okay, so I'll set a true value for the CLK input. As we can see, the Q1 output of the SR1 block stays true, but the output of the R-trig is already false. That's because it only gives an output for one execution, even if the CLK output stays true. Here is also an example on how to call the R-trig block in different programming language. Ladder in FBD and also on structured text. Next that we have here is the Fdrag. It is basically the opposite of R-trig. Instead of detecting a rising edge, it detects a falling edge. The transition of the Boolean signal from high to low or 1 to 0. Again, same procedure. The declaration is done here in the main program. As I have declared, my Fdrag is named as Fdrag1. Then call it in the FBD action. Here I will add an SR block to represent the single output execution of the Fdrag.
build solution, and log in with online change. Here's a graphical display on how the Fdrag operates. The output Q will remain false as long as the input variable returns true. As soon as CLK returns false, or a falling edge, Q will return true. This means each time the function is called up, Q will return false until CLK has a rising followed by a falling edge. Okay, so let's simulate it. Write a true value. Nothing happens. Should be like that. Now, when I turn this off or false, the CLK will detect a falling edge signal. Then we'll have a single execution output that will set the Q1 to true. So that's how the falling edge trigger works. And here's how you call it in structured text. Now let's proceed with counters. Counter function blocks counts either a rising edge or a falling edge of an input. And when a preset value is reached, the block will output a true value. Here I have declared a CTU counter in the main program named CTU1. So this is an up counter. So what this does is it counts the rising edge of an input. Okay, so add another network and call the CTU block. Build the project. And log in. So the counter variable CV will be initialized with 0 if reset is true. If CU has a rising edge from false to true, the function block CV will be raised by 1, provided CV is smaller than PV. Q will return true when CV is greater than or equal to the upper limit of PV. Okay, so I'll set a 5 preset value. So what I will do is I keep on writing a true value of the input up to 5 until the CV is equal to 5, which then will result to an output. Okay, so I'll write 5 true value on the input. As we can see, the counter up now has an output. So to reset the counter, the reset input should be true. And that's how the counter up block operates. Okay, so last one, we'll discuss the CTD or down counter. It is the opposite of CPU, but it still counts the rising edge of the input, and when it is equal to the preset value which has been loaded to the block, we'll have an output. I won't make this discussion very long, so this is how you declare the CTD down counter. Add another network, insert an empty box, and assign the identifier to the empty box. Build the solution and log in. So when the load is true, the counter variable CV will be initialized with the upper limit PV. If CD has a falling edge from false to true, CV will be lowered by 1, provided CV is greater than 0. Q will return a true value when CV is less than or equal to 0. In here, I have just set a value of 3, and I will trigger a falling edge of that down counter. First, I have to write a true value to the load in order for my set PV to be loaded on, and the counter will start counting from 3. If the load is not activated and CV is 0, output is already energized. Now I'll start writing a true value for the CD input. The counter needs 3 rising edge to activate the output. And there you go, that is how the down counter operates. Okay, so that is all for our discussion on the standard function blocks and how to use it on TwinCAT 3. Let's move on with the structured text, operators, and instructions. Okay, so that is all for our discussion on the standard function blocks and how to use it on TwinCAT 3. I hope you learned much today. If you have any questions or suggestions, please do leave a comment below. Stay tuned for the part 2 of this episode where we'll talk about structured text operators and instructions. Thank you and keep safe.
That's it for this video. If you want to learn more about Controtek Smarter Automation, you can visit our website at www.controtek.com. Subscribe to our YouTube channel and follow our social media accounts. See you on the next video!